Okay, good morning. So we've been talking about first order time-dependent perturbation theory. And just to summarize what we've learned, the key things that we've learned, we took a Hamiltonian, we divide it into a time-independent part and a time-dependent part. So H0 is constant. And we know, hopefully, its eigenstates, which we call n, and its eigenvalues corresponding to those, which we call curly E sub n. Okay, and then the question that we tend to ask ourselves is, if we start in one of the states, so we start in the state n at time t0, and we want to end up in the state m at time t, which you can think of as the present time, then you want the amplitude, and then the amplitude you'll take the complex square to get the probability, the amplitude to go from n to m at first order in perturbation theory, starting at time, or ending at time t and starting at time t0, is you got to do an integral. So minus I over h bar integral t0 to t dt prime. And then there's a matrix element, which in general depends on time. And one of the things we're going to be doing today is to work on situations where we're going to know or control what that time dependence is. But then there's also a time dependence that just comes from what we called in the interaction picture, the time evolution, which looks like this: t prime minus the initial time times the difference in energies divided by h bar. So that's the hard part, is computing that. And then once you've computed that, then you want the probability. The probability to start in the state n and end in the state m is the complex square of that amplitude. Okay, so those are the general rules. And now today we're going to be doing some example applications. And each of the example applications that we're going to talk about today is going to be something that will have many sub-applications. Okay, so our first example is that, let's say we have a constant perturbation. So why is it, if it's a constant perturbation, why is it time-dependent perturbation theory? It's because we're going to turn it on at some time. So this turns on at time, and to make things easier, instead of calling it t0, from now on we'll call the turn on time t equals 0. So t0 is t equals 0. And so our perturbation Hamiltonian is just 0 for t less than 0. And it's some constant v for t greater than 0. Okay, and so v, what can v be? I'm not going to be specific about it today. It can be any arbitrary operator as long as it's constant. Okay, but no time dependence. The time dependence is entirely in this step function turn on. And I guess there's one other property that it has to satisfy. If it's going to be part of the Hamiltonian, it should be Hermitian. Okay, and so now in this example, our task is to find the probability. But because n sounds too much like m, I'm going to, from now on, instead of calling them n and m, I'm going to call them I for initial and f for final. And then also for convenience, we're going to define a frequency associated with the transition. So this angular frequency is called omega sub fi for final from initial. And so what is it? It's the difference in the unperturbed energies divided by h bar. So a good thing to remember is that energies divided by h bars give you angular velocities or angular frequencies. And so one way we know that is that was what happened in the harmonic oscillator, for example. The energy levels were h bars times omegas. Okay, so we're going to make that definition, but depending on our mood or what's most convenient at any given moment, we might write it in terms of the energy difference. We might write it in terms of the angular frequency. Okay, so now we can go ahead and do the integral that I mentioned before. We're now going to calculate the transition amplitude at first order in perturbation theory to go from the initial state to the final state. And so there was our factor of minus I over h bar. And now the good thing is that because our v here is defined to be a constant, when I take its matrix element, I can pull that out of the integral. And so here I've got the matrix element between the initial and final state. And then my integral over time has the time dependence, which is nothing other than I omega times our angular frequency times t prime in the exponential. That's all it is. So the good thing about this example is now we can do this integral. Exponentials are easy to integrate. So let's go ahead and do it once and for all. And then we can apply this to lots of other different examples. So when we evaluate this, this is 1 over I times the omega times e to the I omega fit from the upper limit of integration minus 1 from the lower limit of integration. And now to make this a little bit nicer, we're just going to rewrite it. We're going to rewrite it by factoring out half of the exponential and then rewrite the rest of this. Okay, so we've just factored out e to the I omega t over 2. And why would we do that? It's because now this factor is 2i times the sine function. Okay, and so now we're asked to find the probability, so we're going to take the complex square of that. And so one nice thing that happens when you take the complex square is any phase that's involved, you can just ignore. So we're going to be able to ignore this term, this factor, and this I and that I cancel. But even if they didn't cancel, we can ignore them because those are complex phases. When I take the complex square of this, they don't matter. And so summarizing, what happens is when we calculate the probability to go from initial to final state, we get the matrix element. And then there's a factor of 4 over h bar squared. The 4 is coming about from this 2. The h bar squared is coming from there. Okay, and then there is a factor, let's see, there's a factor of sine squared omega t over 2. And then I have another factor in the denominator of omega squared. Okay, so we found this function that depends on time and the angular frequency associated with the transition. And because we're going to be seeing that function a lot, let's give it a name. And the name we're going to give it is capital F. And so what does this thing depend on? One way of saying what it depends on is it depends on the difference in energies, because that's just proportional to the difference, the omega Fi. And the other thing it depends on is time. Okay, and so another way of writing it would be this: 4 over the difference in energies times sine squared t times the difference in energies divided by 2h bar. Okay, and then once we've done that, the nice thing about giving complicated things names is then it makes other formulas simpler. And so now our probability separates into 2 parts. There's the matrix element squared part, and then there's the F part. Okay, and so if we're going to worry about computing this, this first part, the matrix element part, is giving us a selection rule. There's a matrix element selection rule built into that. Which just says that you only get a non-zero answer if the matrix element of the perturbation between your initial and final states is non-zero. So one way of thinking about that is if it's 0, then the initial state really doesn't even have any way of knowing that the final state exists, let alone transition to it. And so you have to have some connection between the 2 states somewhere. Okay, and then the other factor is the time energy dependence of the probability. Okay, and so we're going to concentrate on that for a little bit. Okay, so if we graph this as a function of time, let me do this over here. Let me put my vertical axis for the probability to transition from initial to final state. And my horizontal axis is going to be time. Okay, and so at times less than 0, of course, nothing happens. That's not what I meant to happen. So nothing happens here because the perturbation hasn't turned on. And then once time t equals 0 has been reached, then we go ahead and plug in this probability formula. And so what happens is it's going to be proportional to something that is a square of a sine function. So that part's going to oscillate up and down between 0 and 1. And then we have this factor times that factor that is going to tell us how big it gets. So it's going to do something like this. It's going to start at 0, grow, hit its peak, come back down, hit its peak again, and so on. Okay, and the maximum that this thing gets to, which it gets to repeatedly, is going to be 4 times the matrix element squared divided by the difference in energies squared. So the matrix element is a matrix element of part of our Hamiltonian. So that has units of energy. And then we're squaring that and we're dividing by the difference in energies squared. Okay, and so the important thing to keep in mind about this is this fails if that dotted line is too high or if the answer is too big. So fails if too big. And that's just because we know that probabilities cannot ever be bigger than 1. And so if we calculate this thing and it came out bigger than 1, then it means that first order perturbation theory is no good. And we either have to go to higher orders in perturbation theory and hope that rescues us, which it might not, or we have to find some better way of doing the problem. Okay, and then by the way, there's a slight typo in the notes that I should probably mention here, that in the notes, I called this VW. Of course, V is W, it's just that V is W after the time turns on. So to be consistent, I should have called it V completely in the figure. And so W should be V in figure 15.3.1 of the notes, which I will eventually put on the corrections page for this. Okay, and then the maximum time, or the time when this thing hits its maximum, is pi divided by the angular frequency. And then at time 2 pi divided by the angular frequency associated with the transition, it gets back to 0. And then at 3 pi, it's back to its maximum, etc. Okay, so another thing that you can talk about besides the fact that the probability is oscillating up and down is you could talk about, okay, maybe we're only interested in very early times. So down here, and you notice if you stare at that, it's growing quadratically with time. And in fact, you can see that from this formula. So if I think about what happens to this formula at very small t, at very small t, the sine squared is just the same as its argument squared. And so there's going to be a sine squared, there's going to be a t squared from that. Oops. There's going to be a t squared from that. There's going to be this factor squared, which is going to cancel that squared. The 2 in the denominator, when I square it, is going to cancel the 4. And so it's just going to be t squared over h bar squared. Right? That's taking the limit of this when the argument is very small. Okay, so for very early times, even if it's going to fail later on, for very early times, this can still be a good formula. Because all I get is a factor of t squared over h bar squared, and for sufficiently small t, that probability will certainly be less than, will be as small as I want. And for larger t, though, this is guaranteed to fail. Okay, so another way of expressing all of this is to graph the function f here that we defined. Let's graph this, instead of graphing it as a function of time, let's graph it as a function of energy. Okay, so graph f. Of course, it also depends on the initial state energy, and it depends on time. But we assume those are fixed for the moment. And we're going to be graphing on the vertical axis what that looks like as a function. Let's graph it as a function of E final minus E initial. Okay, and so the shape of this is the following. Let me do it in blue again. Oops. It's got a main peak, and then it's got some little peaks that die off. This is a very rough sketch. Okay, and so we're graphing f here. And we just figured out that the height of this thing is t squared over h bar squared. So that's the maximum value of it. Okay, and that maximum value occurs when the argument is very small, which means when EF minus EI is 0. And so if we go back up to the function here, again, you have to take the limit of the argument being small. But again, you get h bar t squared over h bar squared. So that's the maximum it can be, which is growing as t grows with time. And then if I look at, okay, what are these minimum values, or where do they occur? They occur at 2 pi h bar over t and minus 2 pi h bar over t. Okay, and then there are other minima out here. But the point is that this thing has this main big bump that has most of the probability in it. And that bump occurs between minus 2 pi h bar over t and 2 pi h bar over t. And so if I ask what's going on as time increases, the height of this thing is growing and it's getting narrower because t is getting larger, so h bar over t is getting smaller. Okay, and so if I ask what do I need to do to get a large probability, the main bump in the probability occurs when the difference in energies is less than 2 pi h bar over t. Okay, and so you'll sometimes see it said that this is some quantum mechanical version of violating energy conservation and saying, oh, you can violate energy conservation for a small amount of time. But really, that's not quite what's going on. The energy conservation here that we're talking about is the energies of the unperturbed states, which isn't the real energy. And so if you're saying that energy isn't conserved, you're really just telling a lie, a convenient fiction. You're saying, let me talk about the unperturbed energy as if it were the total energy, and then ask what happens to conservation of that. But there's no reason for the unperturbed energy to ever be conserved. So this isn't really a failure of energy conservation for a time proportional to 1 over, or for an amount that's proportional to 1 over time. But some people like to think of it that way. Okay, so we've got this main bump that's growing, and the reason it's useful to keep that in mind is because as time gets very large, this bump is getting more and more like a delta function. And that can be important if my states are not discrete, but continuous. So let's now suppose, which is very often the case, that my states F are part of a continuum. Meaning, for example, that I don't have bound state energies that are isolated, but instead I have energies that are continuous, like for a free particle. Okay, and we're going to assume that they're not pathological, so that the matrix elements that we're looking at are continuous as I vary my, or as we vary our final state energies. Okay, so in that case, I shouldn't be talking about individual probabilities. I should be talking about probabilities per unit energy. So instead of writing probability, I'm going to write the differential of probability. Okay, but it's going to look like the same formula, except that now I'm going to be integrating over my continuous energy times the density of states. Okay, and then I've got my F function, like so. And so this is just saying, if I really want the total probability, I should integrate over some range of energies. And then if I integrate the right side over some range of energies here, that will give me the probability to transition to a group of states within that range. But then to do it correctly, I should weight by how many states there are in the final thing. So in words, what this factor here is, this is the number of states available between energy curly E sub F and curly E sub F plus a little bit, which we're calling the differential in curly E sub F. Okay, so really this is the same formula that we wrote down before, but now we're going to be summing over all these states, which we're going to turn into an integral. And so we need the number of them. And then we integrate both sides and we'll get a number that we can compare with experiment. Now, in the continuum, what we're going to be doing is we're going to be noticing that this function f had this big bump that's getting more and more like a delta function bump. And so this factor here, this factor of f approaches a delta function. And the only thing we have to be careful of is to get the normalization of the delta function correct. Okay, so to normalize or to properly normalize the delta function from f. So one thing we know about delta functions is when you integrate over them, you're supposed to get 1, right? And so we're going to integrate over our function f in energy over all possible energies. Now let me write down my function f. It's sine squared final energy minus initial energy times t over 2h bar divided by final energy minus initial energy. I'm going to put my 4 in the numerator in the denominator like that. Okay, and that's an integral that you can actually do because it's a definite integral. We're integrating over all E sub f. And so when you work it out, this comes out to something nice, namely 2 pi over h bar times t. So notice it doesn't depend on the initial energy. It doesn't depend on the final energy because we're integrating over that. It also doesn't depend on the initial energy because it only appears in a combination of EF minus EI. So it comes out to that nice simple thing. And so if this were a delta function, it should have had area 1 under it instead of 2 pi t over h bar. And so what that's telling us is that when we see the function f, and we're going to take the large t limit, we can replace it by 2 pi over h bar t times the delta function in EF minus EI. Okay, and the arrow means this works for large times. Because it's only at the large t limit that this thing starts to act delta function-like because it's getting taller and skinnier. Okay, so this is our rule for how to deal with our function f. And this thing, remember, appeared in the expression for the probability. And so let's think about what that means. We've got a probability that at large times is proportional to time. And so if it's proportional to time, that means that it's a rate. What we're really computing here is a rate, a probability per unit time. So another way to say that is the differential contribution to the probability to go from the initial to the final state is t times a differential rate, which is traditional to call that gamma. Okay, so d gamma is a rate. Okay, and basically by pulling off all the factors that we've got here, we have figured out what that rate is. The differential contribution to the rate to go from the initial to the final state is 2 pi over h bar. That came from here. We've stripped off the t, so we're not including that. We also had our matrix element. Okay, we have our delta function that comes from here. That's saying at very late times, the initial energy and the final energy have to be the same. Okay, and then what else do we have? We have back up here, we have our density of states and our energy that we're supposed to integrate over. So writing those two things down, there's density of states and our differential of energy. So by the way, when applying this to more specific examples, a lot of times the difficulty, the really hard part is getting the density of states right. Right, delta functions we know, matrix elements can be hard, but usually you set up the problem in such a way that you know the matrix element or you can compute it. And you can do the integral, but what you really need to know that might be tricky is the density of states. Okay, now this is a very famous formula in quantum mechanics. This is known as Fermi's golden rule. And of course, it's known as Fermi's golden rule because it was invented by Dirac, not Fermi. But Fermi was the person who sort of popularized it. It's very important in science to get credit for things other people do by popularizing it under your own name. Now, Fermi didn't really cheat. He always was careful to say, yeah, this is Dirac's idea, but he's the one who explained to everybody else how to use it. Now, in fact, it's a little bit tricky to know how to use this because what we've got here, it does in fact involve a delta function. So in this form, you're never actually going to get a number out of this directly. What you have to do is you have to do some integral to apply it. Okay, so to do, in other words, for a group of states which are forming a continuous group with energies that are close to the initial energy, the total rate for transition is going to be gamma. It's going to be 2 pi over h bar, matrix element squared. And then when we integrate over the final state energy, we're going to get our density of states, but we're only going to get that for the final energy equal to the initial energy. That's what the delta function is telling us. Okay, and so to get that thing I've just written down, what you've really done is you've integrated your differential in rate over the overall possible energies. So this is really the equivalent of Fermi's golden rule. And that version of it is maybe slightly more practical because that's an actual number rather than being something involving a delta function, which is just 0 or infinity. Okay, so to use this equation, we've integrated over final state energies. Notice it's valid for large times, but not too large. Right, because we're saying there's a probability per unit time, and eventually if the time gets too large, that probability as it's growing linearly with time will exceed 1. And so what we mean by too large is this is not valid for times t that are greater than 1 over gamma. So if you compute your gamma, you're allowed to say that's the rate for transitions as long as that number is smaller than 1. Or actually, it's probably much smaller than 1. Because when it starts to get near 1, then that's a sign that you should be going to second order in perturbation theory. So we've applied this, or we derived this, assuming the final states were continuous. Okay, and so this is also okay if the states are not quite continuous, but very narrowly spaced. So this is okay if the level spacings between different final states obey that the time t is much, much less than 2 pi h bar over the spacings in energy, right? So we've got a bunch of states here, and the spacing in energy is delta EF. As long as that's small enough, then you're okay. Okay, and the reason for that is because if you've got a very large number of states all closely spaced in energy, then you have lots of states underneath the bump that we turned into a delta function, and it looks just as if it was continuous. Okay, so okay if level spacings, because then you have enough states under the bump. The bump means the bump in the F function. Okay, any questions on that first example before we go to our second example? All right, so our second example is going to be actually looking a lot like the first one, but this is harmonic perturbations. So once again, we're going to assume that that before some time t equals 0, we have no extra Hamiltonian. Oh, by the way, why do we care about this? This includes things like electromagnetic waves, which we will get to, interacting with charged particles. And to see why, let's just write down what our harmonic perturbation looks like. Okay, it's going to be 0 for time t less than 0. And it's going to be this thing, v e to the I omega t plus v dagger e to the minus I omega t for t greater than 0. Okay, so there I wrote an operator v, but v here doesn't have to be Hermitian as long as I include v dagger. And when I take the Hermitian conjugate of v e to the I omega t, that's going to be v dagger e to the minus I omega t. So the sum of those two things will be a Hermitian operator. And then once I've done that, I can write this as sines and cosines and that as sines and cosines. So really the whole thing is some linear combination of sines and cosines times v and v dagger, which we're going to be assuming are constant in time, but otherwise arbitrary. So we're just saying that all the time dependence can be summarized in terms of an angular frequency omega. So we have to be careful. This angular frequency is sort of the driving frequency of the perturbation. It's different from the angular frequency we were talking about before, which was set by the initial and final states. Okay, so we know what to do. We write down our integral for the transition probability amplitude. It really just depends on time because we've set t0 to equal 0. And it's equal to minus I over h bar. We have to do a dt prime integral. And now there are two parts to this. There's the v part. And it has this time dependence on it. And then there's the V dagger part. Okay, so the exponentials of t prime, the first part of each of those just came from our general formula for the transition amplitude. And then the omega part is coming from the perturbation that we're putting in. But the nice thing about it is because they're both e to the I t primes, we get combinations of those different angular frequencies. So when we do the integral, we've actually already really done the integral. Okay, this is going to be 1 over h bar VFI, that's what I'm calling the matrix element, right? So this is VFI here is the same thing as that. It's just a shorthand notation. And then there's a factor, we've already done the integral, it was just with a different combination of omegas. Okay, all of this over omega f minus omega I plus omega. And then there was V dagger Fi. And it looks almost the same. It's just that omega is coming in with the opposite sign. Okay, and now everything is going to be pretty much the same as what we did in the last example. It's just that we have these extra omega parts. But there's one important difference that we have to talk about. And that is, because we're going to be talking about large T, what we're really interested in is the resonant part of this expression. So for large T, remember we got a delta function. And so the first term in the preceding line.
Was that a W? Was that a WI, that second term in the denominator?
Yeah, thank you. Forgot my I there. Good. Okay, so the first term is resonant, meaning it's going to have a delta function that's going to make it non-zero if omega f minus omega I is equal to minus omega. In the previous example, it was just 0, but now it's minus omega. Okay, and the second term is resonant if omega f minus omega I is plus omega. And we want to be concentrating on examples where omega is not 0, because if omega is 0, that was the previous example. So at most, one of these terms is important in any given situation. Because omega f minus omega I can't be both omega and minus omega at the same time unless omega is 0. So what that tells us is that we get to ignore the cross terms between these two terms when we square this amplitude. Okay, so ignore cross terms, which is a big help.
I'm sorry.
Normally in quantum mechanics, you're not allowed to ignore cross terms when you square amplitudes. But in this case, we can get away with it. And the reason we can get away with it is because we're imagining waiting for a long time. For a long time, we get a delta function. The delta function is telling us that two terms cannot both be non-zero.
I'm sorry, Professor, I got lost. You said, okay, at most one is important.
Right.
So could you just explain this one more time, please?
Okay, so we've got two terms here. So I'm saying one of these two terms can be important, but at most one. And the reason at most one can be important is because it's either the first term is important if that's true, or the second term is important if that's true. But those two things can't be true at the same time because we're assuming that omega is not 0. Okay?
So, by important, you mean they're in resonance? Is that what you mean?
Right. Maybe, in fact, instead of important, I should have just said non-zero. Really important at large times, and then in the ultimate limit of very large times, only one of them will be non-zero because of the delta function, which I'm about to write down.
Okay, thank you.
Okay. So, let me first do an intermediate step, which is the probability to go from I to F is, so everything here is just the same as what we did in the previous example, except there's two terms involving matrix elements. And this one has omega F minus omega I plus omega times T over 2. Okay, and then the other one, we're just writing all of this out for the record. It's exactly the same thing, so I won't write it again, except that there's a minus sign for the omega. But otherwise, it's the same. Okay, and those things are really just our functions f again, but with a different argument. So these are VFI squared times f of EF minus EI minus h bar omega. And then as a function of time. And then the second term is this plus h bar omega times t. And so that's what I mean by in the large T limit. So for large T, but not too large, because you don't want the probability to be larger than 1. Then we're going to get a probability, which is again a rate times time, just exactly the same way we did it before, where the rate is, or the differential contribution to the rate is 2 pi over h bar, our density of states, our differential in the energy. Okay, and then we have our matrix element, which we're writing in shorthand notation, times the delta function. Should be minus h bar omega, I think. Okay, and then the matrix element for V dagger squared times a different delta function. Okay, so really we could just separate those two terms because they can't both be non-zero at the same time. And so the names for the two terms are stimulated emission That's the name we given to the term that contributes when E final is equal to E initial minus h bar omega. That's when you lose energy h bar omega to the potential. And absorption is when it's the other way around. That's when the final energy is equal to the initial energy plus h bar omega. So you gain energy h bar omega from V. Okay, so you're not really violating energy conservation, of course. What you're talking about here is when we say lose energy or gain energy, we're talking about the unperturbed states, which are not the exact states of the system. Okay, so this is another version of Fermi's golden rule. This is Fermi's golden rule for harmonic perturbations. It looks very similar to the Fermi's golden rule for constant perturbations. Constant after time t equals 0. And it's valid in a slightly larger set of cases, though. So it's valid in two real situations. One is if the final states have continuous energies, or they're continuous states with continuous energy eigenvalues. But for harmonic perturbations, so that was the case for the constant perturbations too, but for harmonic perturbations, there's another case where this is also valid, and that's if the perturbation frequencies are continuous. So the formula is valid as long as you have something to integrate the delta function over. And so in this case, if the perturbation frequencies omega are continuous, then you would integrate that expression over the frequency, and that would get rid of the delta function and give you a number. Okay, so we're out of time today, but we'll talk a little bit more next time about applying this formula for the case of harmonic perturbations. And then the real reason that what this is all setting us up for is to talk about interactions of atoms with electromagnetic waves. So we will do that by, basically that will be specifying what our V's are. And so we'll hopefully get into that on Wednesday. Okay, any questions about today's lecture? All right, and if not, I will see you all on Wednesday.
Thank you. Thank you so much.
Professor, I'm just